Okay, so this is a video on using the derivative to calculate matters that involve particle motion. Okay, so there's some key ideas here that if some function s of t is a position function, so it gives its position at time t, then usually s prime of t is the velocity of that particle, which is directional. And then if I take s at t2 and subtract s at t1 and put that over t2 minus t1, this is actually going to give me the average velocity. So the average velocity over the closed interval t1, t2. So that's given by that ratio, which is basically its slope. It's like the slope of the secant line over that period. If I take either the absolute value of the magnitude of the derivative, I get the speed of the particle, right? And if I take the second derivative, I get the particle's acceleration. Okay, so there's two cases that these problems show up in BC Calc, and we'll take a look at both cases here. And so the first case is a one variable or one dimensional case, and in this case it's kind of like you have a string with a bead on the string, and x of t gives the position of that bead. So if different times t, that bead is going to be at different locations along that string. So x prime of t is the velocity of the bead, which means that it is giving the rate of change in the positive x direction, or as it is going to the right. So if velocity is positive, the bead is moving to the right. If velocity is negative, it is moving to the left. xt2 minus xt1 over t2 minus t1 is giving me the average velocity. So this is the average rate of change as the bead is moving to the right. Now if I take the absolute value of x prime of t, that's going to give me speed. That's not just average rate of change to the right, but that's average rate of change in any direction, whether it be left or right on the string. X double prime of t is the acceleration of the particle as it's moving to the right. Okay, so a quick note of something. If the sine of x prime of t is equal to the sine of x double prime of t, so the acceleration and the velocity have the same sign, then speed is increasing. If the sine of x prime of t is not equal to the sine of x double prime of t, so if the acceleration and the velocity have different signs, then in that case speed is decreasing. So velocity and acceleration have the same sign, speed is increasing. Velocity and acceleration have different signs, speed is decreasing. Okay, so let's look at the second case here. Okay, in the second case you have a two-dimensional, so you're going to have a two-dimensional space with two variables, right? So we're looking at here is something that's happening in the xy plane because it's two-dimensional. You have a vector that's going to give position. So this is going to be the position x at time t, y at time t. If I have a vector r at t that is x of t, y of t. This is a vector that gives the position of a particle at time t. So we can call that a position vector. If I take the derivative of that position vector, I'm going to get a two-component vector again, and this is the rate of change. It's going to be the rate of change to the right and the rate of change up of this particle. Okay, so if I want the average rate of change over a particular period, I take our vector r prime t2 minus r prime t1 over t2 minus t1. So this is again going to give me a vector, but so where this was the velocity vector, this is the average velocity vector. So this gives me the average rate of change up and to the right. If I take the magnitude of r prime of t, so this is going to be the square root of x of t squared plus x prime of t squared, y prime of t squared, right? So this is the magnitude of the derivative vector. That is the speed of the particle. So it doesn't matter what direction the particle is going in, I have its instantaneous rate of change in any direction. And finally, if I take the second derivative of r with respect to t, that is the acceleration vector. Alright, so let's look at some examples of this and see if we can kind of map this out a little bit. Okay, in our first example, we've got a position vector a position equation where this is the one-dimensional example, where we have x of t being t cubed minus 12t squared plus 36t plus 18. So let's say we want to know when this thing is going to change directions. So that's going to involve the velocity. If I take the velocity of this, I get 3t squared minus 24t plus 36. Right, well, let's look at when that's equal to 0. So if I set 3t squared minus 24t plus 36 equal to 0, I have a common factor of 3. So that's t squared minus 8t plus 12 is 0. This is a factorable polynomial. T minus plus, sorry, that's not correct, it's minus minus. Right, they have to add to negative 8 and multiply to 12, so that would be 6 and 2. So when t is equal to 6 or t is equal to 2, we can have a change in direction. If you were to build a sign chart for this, with the 2 and the 6 here, we're assuming that my journey starts at 0 and goes off to infinity in time. From 0 to 2, my derivative, my velocity is positive, so I'm moving to the right. From 2 to 6, my velocity is negative, I'm moving to the left. And from 6 to infinity, I am positive, and I am moving to the right. So the direction changes at t equals 6 and t equals 2. If I substitute the 2 in for the x equation, I get 2 cubed minus 12 times 2 squared plus 36 times 2 plus 18, which happens to work out at 50. And then times 6 is going to be 6 cubed minus 12 times 6 squared plus 36 times 6 plus 18, which happens to work out as 18. Okay, so at time 0, my particle is hanging out at 18. It starts moving right for 2 seconds, and at that point it hits 50. And then it moves left for 4 more seconds, which gets me to time 6, which puts me back at 18, exactly where I started. and then it starts to move right again and goes off to infinity. So that gives me a sense of the motion of that particular particle. Okay, so let's say we want to know when that same particle, the one whose path is being determined by x of t is t cubed minus 12t squared plus 30t plus 18. Let's say I want to know when this thing's speeding up and when it's slowing down, right? So let's see, let's take x prime of t again, which is 3t squared minus 24t plus 30, right? And 36, that should be 36, there we go. And I want to know x double prime of t, right? So that's going to give me what? That's going to give me 6t minus 24. All right, so we got the sign chart for x prime before, right? So that sign chart just said make a change at 2, make a change at 6, start at 0, right? And it was positive up until we got to 2, negative until we got to 6, and then positive out to infinity. The point of change here, so like for the second derivative, 6t minus 24 is 0, 6t is 24, divided by 6, t is 4. So the second derivative, so this is the first derivative, this is the second derivative, is changing sign only at 4, right? So we have, to the left of 4, we have negative acceleration. To the right of 4, we have positive acceleration. So what we want to look at is when is this thing slowing down and when is it speeding up. It slows down when the signs are different. So I'm slowing down on the interval 0 to 4. And the signs are again different on the interval from 4 to 6. Or sorry, so they're different on 0 to 2, not 0 to 4. 0 to 2, because they're the same sign. From 2 to 4, they're both negative. And from 4 to 6, we have different signs, negative, positive. So that's where it's slowing down. We speed up on the interval from 2 to 4 because they're both negative. So that's speeding up and going to the left. And then from 6 out to infinity, we keep speeding up as we're moving to the right. Okay, so that gives me a little semblance of what that particle's doing. Let's look at the two-dimensional case. All right, so let's give a position vector for the two-dimensional case. So r of t will be negative 1/2 t squared t, right? So let's try to figure out what the speed of this particle is when t is 2. Okay, so to get the speed, we need the velocity. So let's see, this first term works out to be negative t, right? And the second term just becomes 1. So the velocity at time 2 should be negative 2, 1. The speed at time 2, right, should be the square root of negative 2 squared plus 1 squared. So that's the square root of 5, which is approximately 2.236 units per second. So that's the speed in this direction of negative 2, 1 at time 2. Alright, so that's a little bit second or two-dimensional game there. Let's look at something else that's a possibility here. Let's say I have a particle that starts at time 0. So t is always going to be greater than or equal to 0. It's going to follow a path where r of t is given by the vector, the position vector for t, negative 2t. Alright, so we want to know the shape of this path. So let's think for a second here. If I take the velocity vector of this, I'm going to get 4, -2, right? So this tells me that dx dt is 4, dy dt is -2, which means that dy dx is -2 over 4, or -1/2. So this is a constant rate of change. So this particle has a constant rate of change. It's not dependent upon t. That means my path is linear, because it has a constant rate of change. Okay, so a little algebra 1 there. And then, but t is greater than or equal to 0, so it has a starting point. So if I have something that has a starting point, let's give this a little bit more accurate representation, right? Because this is -1/2, right? So this thing's going to go downward. So it's going like down 1 for every 2. So it's going to kind of look like that. It's going in that direction. There's the shape. This thing is a ray. Okay, it has an endpoint and it goes in a linear fashion in one direction. That means that the shape of this curve over that domain is a ray. Alright, so that's pretty simple, straightforward. Could be a great BC multiple choice question. So this brings me to one of my favorite free response type questions. We have a curve that's moving along a path that's defined by x of t is 2t, y of t is 36 minus t squared. Okay, and I'm fixed in the domain 0 is less than or equal to t is less than or equal to 6. And I have some particle here. This thing's on some curve. I don't really care how that curve goes. I could be more accurate with my drawing. But this particle is on some curve from time t equals 0 to some time t equals 6 seconds later. And here's what's happening, is that this particle has a laser light on it. And that laser light is going to show on the direction of its motion. So the tangent to the particle at any given time. And then it's going to show on the x-axis. So that light is always pointing at the x-axis to a very particular spot. Alright, so there's a couple questions that come up in this free response question. 1, what is the velocity of the particle? Okay, so if I want r prime of t, then the derivative of x is 2. The derivative of y of t is -2t. So this is my velocity vector for the particle in space. Okay, so now I want to write an equation for this line. So I want an equation for the tangent line. And I want to do this in reference to t. Okay, so dy dx, the slope of that tangent line, is going to be -2t over 2, which is just -t, right? So y minus the y value at time t is going to be 36 minus t squared is equal to the slope, -t, times x minus the x value at that time, which is 2t. So you gave me a value for t, and this is going to give me an equation for that line, depending on where that particle is on that curve. Okay, so the third part of the problem asks, can I figure out where this point is on that line? So remember, if I'm on the x-axis, y has to equal 0. So that's going to make that 0, right? and moving some things around here. Let's see, I have now negative 36 plus t squared is equal to negative tx plus 2t squared, right? So let's see, that's going to put the tx over here. Tx is equal to now t squared plus 36 when I bring this over there and the 36 over there. Divided all by t, x is t squared plus 36 over t. So this is interesting. Now I know where this location is on the x-axis at given time t. So I literally have that location as x of t is t squared plus 36 over t. Okay, so the last interesting question that I might ask here is, what is the speed of that beam going along the x-axis at time t? And let's say we want to know it for time t equals 3. Okay, so in order to find the speed, I need the derivative of this. So I could write x of t as like t squared plus 36 times t to the negative 1. Right? Take the derivative of that, x prime of t is going to be, well, let's see. That, I think, is... wait, I can do a little bit of thinking here. Before I do that, let's make this simpler. Let's distribute that t to the negative 1. That's just going to make that t plus 36t to the negative 1. Aha. So x prime of t then is just 1 minus 36t to the negative 2. Right? So that's there. Let's see, x prime of 3 then is 1 minus 36 over 9, which should be 1 minus 4, which is negative 3. But if I want the speed, I take the absolute value of that, which is the absolute value of negative 3, which is 3. Okay, so we've gone from these parametric equations to the slope of that tangent line, right, to the formula for the tangent line, to the location of where that tangent line crosses the x-axis at any given time t, to the speed of the light moving on the x-axis as the particle is moving around this curve. So at time 3, as the particle is moving along this curve at time 3, the light on here is actually going to be moving at 3 units per second. So take some time to sit with that one. It's a bit of an extensive problem, but I think it's an awesome idea that shows both a two-dimensional and a one-dimensional situation all in the same problem.